Hello, everyone. Today I'm going to talk about the interpretable natural language processing. This is the 12th lecture of natural language computing. In the past few years, you have seen increasingly powerful natural language processing systems that are deployed to an increasing number of roles in people's lives and works. Naturally, this gives rise to concerns about the trustworthiness. In this slide, I'm going to explain two aspects of the trustworthiness: transparency and accountability. For a developer of a system, one of the worst nightmares is that it doesn't work, I don't know why, and it works, I don't know why. So in this case, the system is lacking transparency. We do not know how it works. For the non-developers, for the users and other stakeholders, we cannot trust a system if we do not know how it works. So only a transparent system is trustworthy. Another aspect of trustworthiness is accountability. It is not 100% of the case where the systems always succeed. When it fails, we need to know why it fails, and further, how can we improve the system? If the system has no accountability, then essentially it's not trustworthy. So people won't trust a system with poor transparency and accountability. When developing and deploying AI systems, the concerns about the trustworthiness leads people to improve these aspects. In addition to transparency and accountability, there are additional terminologies that are floating everywhere. For example, explainability and interpretability. An explainable system is essentially it's transparent. Every component of the pipeline is explainable. So it is transparent and people know what happens inside the model. This requires a special method to build the component of the model. So usually the performance of the model is going to be limited. Some very simple models are explainable. For example, linear regression and decision trees and some one-layer or two-layer neural networks. But nowadays, most high-performing systems are based on very deep neural networks, and themselves are by no means explainable. So we need additional techniques to post-hoc reveal the intrinsics to the humans. And the approaches that post-hoc explains the intrinsics to the humans belongs to the interpretability method. So there are some debates on the exact meaning of these terms, but in this lecture, let us just adopt a broad definition for interpretability. So the research along this direction involves everything that makes an AI system more trustworthy to humans. By everything, I mean literally everything, from the model building and how to present the results to humans, and the data, and essentially everything along the pipeline of developing and evaluating this AI system. Note that there are some overlaps between the interpretable NLP and explainable NLP. The methods that can make that can build an AI system can also be classified into interpretability methods as well. So in this lecture, we are going to briefly look at Shapley, which is a method for attributing the importance to each feature, probing, methods for post-hoc analysis, and natural language explanation. we'll also look at how to evaluate those interpretability methods. An overall principle of explainable AI is to find a simplification of the models using some proxies. Simplification essentially leads to trustworthy. You have heard about arguments that artificial general intelligence will take over the world, but nobody says that linear regression will take over the world. Although there are significant overlaps between linear regression and artificial general intelligence. In a linear regression model, the features are transparent. For a trained model, you know the importance of a feature. The importance of feature xk is exactly beta k. And we can attribute the prediction of the linear regression system to xk with the importance beta k. And further, with ANOVA, we can compute how much of the variance in the output could be explained by the variance in this input. So how to compute the importance score of each feature to a non-linear model? Here we use Shapley value. This is an approximation that can be applied to non-linear systems. Imagine there are the n features are the n players playing a game with y as the result. So the expected contribution of each feature is the importance of that feature. In other words, the Shapley value describes how much this feature can change the prediction. The author won the Nobel Memorial Prize in Economics in 2012. So if a player does not change the result of a game, essentially it is not important. So this is in this mean, for those who are not familiar with the Golden State Warriors, they won the champions in 2015, and then a person called KT, which is the left one in the min, came in the summer of 2016, and then they won the champions in 2017 and 2018, and then he left. In 2022, Golden State Warriors won the champion without him again. So you can make some inference about the importance of this player to the team. Okay, enough jokes. Let's get to the computation of the Shapley value. Let's consider a set or a collision of players that do not contain the target player, xk. So let's write that as S. So S consists of a collection of players that do not contain x of k. And let's denote the outcome as y. So we are interested in the difference between the collision with this player and the outcome with the collision without this player. So for each of the collision S, we're interested in this difference, and we take the expectation over all the possible combinations or all the possible collision, and this is the Shapley value. How to compute this expectation? Let's count how many possible scenarios out there. So for the on this slide shows a possible combination. So let's say the S or the target set S is on the left hand side, as marked as gray area. There are the cardinality of S, number of players out there. And on the middle shows the target player XK. And on the right-hand side shows the remaining players. And there are n minus 1 minus cardinality of S players on the right-hand side. So how many possible scenarios out there that can form this combination? There are so for the left-hand side, there are the factorial of cardinality of S. And on the right-hand side, there are the factorial of the n minus 1 minus the cardinality of S. And these two sets are independent. So we can multiply the number of conditions of the left-hand side and the right-hand side. And overall, how many combinations are there to for the n players in total? There's n factorial. So you divide the number of conditions that can form this combination by the total number of possible scenarios, which is n factorial here, to get the probability of this set. And now you have the probability of this combination S. You multiply the probability with the difference of with the difference of the game outcomes, and sum them up by all the possible collisions. So this will give you the Shapley value. The Shapley value computation is very, very expensive because there are exponential number of combinations out there when selecting the player set S. So some popular toolkits use Monte Carlo sampling. Instead of traversing all the possible S, you select some collisions by some systematic sampling. And there is a popular tool, SHAP, that encapsulates the computation of all of this. Another method is post-hoc prediction, where we call it probing. Probing methods inspect the representations of the deep neural network models. In a broad sense, probing can sometimes be used to refer to any methods that try to understand what happens inside the deep neural network models. But here we take a narrow sense. Probing refers to the method that applies some post-hoc prediction models like logistic regressors or two-layer neural networks, some very simple prediction models to try to predict something out of the model's representations. So the machine learning people like to say garbage in, garbage out. So if the input to the machine learning models have low quality, they're not informative, they are very convoluted, and the features are very useless, then it's very, very hard to get an output that matches the prediction target. Same applies to probing. So if you replace the input from the features with the representation of the deep neural network models, similar principles applies as well. So if it's very hard to get the predictions right, then that means your input or the model's representations are garbage. So intuitively, if you observe very good predicting accuracies or very low cross-down entropy losses from the post-hoc prediction, then that means that the representations that you pass into the logistic regressor is very informative. Probing can examine the linguistic abilities. On this slide shows an example of what result you can expect to observe from probing analysis. So if you take the representation of a very deep model like BERT, you take the representation of layer 4 and dump that into a logistic regressor. And you can use the prediction accuracy to describe the targeted linguistic ability. So probing involves a machine learning data set. Let's say this data set tries to predict the syntax structure. So one possible setup is to try to predict the part of speech. You input a sequence and you try to predict the part of speech at the first or the second and the third, and at every single location. So if the part of speech prediction can reach 90% accuracy, then a reasonable conclusion to be inferred from this probing analysis is that this layer contains sufficient information to encode the one aspect of the syntax structure, like part of speech, with this amount of accuracy. So you can take one step further and say that this part of this model has some extent of the syntax ability. Same applies to the tense prediction. So if the representation of this layer can be used to predict the tense well, then you can say that this model contains sufficient ability to encode the tense. Since the probing results are useful, we can use it further. In the last slide, I have shown you that the probing analysis can be used to give a collection of scores to describe the various linguistic abilities of the model. For example, the syntactic tree depth at layer 1 is 0.7. This means that the probing test accuracy at the tree depth probing task is 70%. So you have a collection of the probing tasks, and you have a collection of accuracy scores that describes the linguistic abilities on multiple dimensions of this model. In one recent paper, we find that this collection of vectors can be used to predict the fine-tuning performance. So when developing the models, the model developers usually care about the downstream performance. They fine-tune the models and try to reach as high accuracy as possible, but there is a limitation for the model. There is if the model, for example, as determined by the initial state and the parameters and the structural limitations, it has some intrinsic limitations, and no matter what you try, you can only reach downstream fine-tuning accuracy of 0.95 on the QNLI dataset. Is that possible to kind of infer or predict the downstream performance without going through the painstaking processes to develop the models in the downstream fine-tuning processes? In this paper, we showed that it is possible. You can just take the probing results and apply some linear regressions. And this regression can reach the root mean square errors that are much better than the regressions from the random features. So the takeaway story is that the multidimensional evaluations are helpful. And they are helpful for example, resuming from from checkpoints and tune the hyperparameters. That's enough for probing. Let's get to the last section of this lecture, which is natural language explanation. Here is my favorite question that tests the common sense knowledge of the large language models. This question comes from the Winograd Schema Challenge. An elephant cannot be put into the fridge because it is too large. What is it? Is that an elephant or is that the fridge? To correctly select the answer elephant, you need to provide the common sense knowledge that an elephant is too large to be put into the fridge, so that the pronoun it in the question refers to the subject, an elephant, instead of the noun, the fridge. So explanation can help provide some common sense knowledge. And common sense here refers to the information or the content that are not present in the question or the answer. Here's another example of the natural language explanation. Where do the winners of the 2018 Turing Award work? The answer is U of T, UDM, and New York University. The explanation is that the winners of that Turing Award are Jeffrey Hinton, Yoshua Bengio, and Ian LeCun, and they work in U of T, UDM, and New York University respectively. So this is a two-hop reasoning process, and in order to reach the result and answer this question, you need to make two hops out there. The first hop queries the winners of the 2018 Turing Award, and the second hop queries the location where each of these three researchers work. So explanation can provide reasoning step and complete the hop. Another aspect that natural language explanation is useful is that they can provide post-hoc rationalization. Let me explain what post-hoc rationalization means. Imagine that you are using a search engine. You search for a bike, and among those list of results, you see a helmet. Why? Because one of the explanations can be a helmet makes the bike ride safe. So this explanation rationalizes the event. It makes this event less surprising to the humans. And I say it's post hoc because this explanation has nothing to do with the search engine itself. The search engine can be Google, it can be Amazon, it can be anything else. And it can be based on features, it can be based on deep neural networks. It doesn't matter. As long as the question, the scenario is out there, and you want to see the why a helmet is returned among the list of results, this explanation could be used to, could apply. So this is what post-hoc means. As a side note, this explanation is very high level. There are other possible explanations out there that are a lot more detailed than this high level explanation. I'll elaborate in a few slides. And as a side, Nisbel and Wilson in 1977 argued that how we explain ourselves is similar to how we explain the behavior of others. So as humans, in many decision-making scenarios, we first make the decision and then find some reasons to justify ourselves. And we use some reason to explain ourselves to other people so that our decisions could potentially be understood by others, regardless of whether we are using the reasons ourselves to make the decisions. So even if we make some very bad decisions, we tend to explain ourselves to other people with some post-hoc rationalization method. Okay, enough for the human's explanation. Let's try to see if machines can be used to generate the natural language explanation. Here's an example. We put a prompt into the explainer, which is usually a large language model. The prompt is constructed in the special format. So you write the problem, you write the you write some functional words, and you insert a word because, and let this model continue generation after this prompt. Sometimes if the model or the explainer is powerful enough, it is able to output a string that to some extent explains the problem in your input. And we need some prompt engineering here. This is what some popular models can do. DaVinci 3 can, DaVinci 3, right? It is a metaphor for something that is too large to fit into a tight or small space. This somehow makes sense. And let's take a look at ChatGPT. ChatGPT, right? An elephant is too large to fit inside a standard size fridge. In general, it is not advisable to put large animals such as elephants inside fridges, as they would not have enough room to move around and could potentially harm themselves or damage the fridge. It first explains the question and then continues to write and elaborates on some additional details that are relevant to this scenario. So I personally think ChatGPT can give acceptable explanations just by continue writing after this prompt. So as an aside, the explanations are not always suitable for everyone. Imagine the scenario where you search for a bike and got recommended a helmet. You get a very detailed explanation. So if you are a very detail-oriented person, then you might consider this explanation to be acceptable and convincing. But if you are just casually looking around, you probably will not even have time to finish reading this explanation. So this explanation, although it's convincing, it provides sufficient details, it provides the reasoning steps, and it provides sufficient justification. It's not suitable for the busy customer for the customer who just want to look around. This is the suitable explanation for someone who just wants to casually look around. Help me make the bike ride safe. You just want to see some sentences that are no longer than 10 words if you only have 1 second to read. So, in that paper, we use some prompt engineering methods to adapt the generation of the explanations towards different scenarios. And we also use some scores that evaluate how well the generated explanations could fit into different scenarios. If you're interested, I will send you the link to the paper after the class. So let's also briefly look at how to evaluate those interpretability methods. There is the model-centric evaluation and the human-centric evaluation. For the model side, we automatically compute some scores. For example, do the explanations, whether they are attribution scores or they are probing results or they are natural language explanations, do the explanations help improve the downstream model performances? How much the task-specific information is provided by the explanation? How much does the performance change if we remove the highlighted features? There are many other model-centric evaluation methods. Same applies to human-centric evaluation. How do the decisions of humans change if we provide them with some automatically generated explanations? Do the human users consider this AI system to be more trustworthy if the humans see this explanation as well as the models, the AI system's result? Do the humans consider the models more trustworthy when they see the intrinsic mechanisms of this model? So there are many other interpretability evaluation methods. And the methods listed here are those more common evaluation methods. So by the end of this lecture, you should be able to describe Shapley value probing and a method to generate natural language explanations. You should be also be able to describe some methods for evaluating how well the methods to explain the AI systems work.